Hey y'all, this is the last section for Unit 9 over transformations. And so we're going to be talking about something really simple with symmetry that you learn when you're really little. And then we're going to be talking about dilation. So it should be pretty quick. So a figure has symmetry if there is an isometry that maps the figure onto itself. So for instance, you have a heart, right? And you fold it over on the line of symmetry, then there's an isometry that maps the figure onto itself. The three types of symmetry that we're going to talk about today are reflectional. That's the one that we think about all the time. But then there's also going to be rotational, and then there's going to be point. Okay, so make sure you understand all three of those really well and that you have those defined. So the first one is the one that we see all the time is reflectional, a figure that has a line symmetry if and only if a reflection maps the figure onto itself. So you think about a heart, right? And it has that line of symmetry that if you were to fold it over, it would be mapped onto itself. So that is line symmetry. Just think you're drawing a line down it. Rotational symmetry is going to be a figure that if you rotate it, it maps the figure onto itself if it is a turn of less than 360. Because anything that you turn 360 degrees is going to be the same exact thing. But let's say we take that heart, for instance. Any way I rotate that heart, it's never going to look exactly the same until it goes all the way around. And so, for instance, we're going to see with a heart, it's not going to have rotational symmetry because it takes 360 degrees for it to look the way it does right now. The last one is going to be point symmetry, and it is a figure that if you rotate it 180 degrees, then it maps the figure onto itself. Okay, so anything that has, we're going to see here in a minute, anything that has point symmetry must have rotational. So anything that has point that can go 180 degrees onto itself, then it must have rotational symmetry because 180 is less than 360. Okay, but everything that has rotational isn't necessarily going to be exactly 180 degrees. And so we'll see that. The way that we're going to get the angle of rotation, because it's going to ask you for that, is you're going to take 360 and divide it by the order of rotation. So here's what that means. If you have a star, okay, so I'm going to draw my best star right now. Okay, that's pretty bad, but not terrible. If I rotate this, it should, now I know mine looks bad, but if it's a good star, if I turn it, basically it has 5 points. Anytime I turn it, out of those 5 times, it's going to look exactly like it does right now. And so what I would do for a star is I would do 360 divided by 5, and that would get me the angle of rotation. Okay, so it just kind of depends how many points you have, but it has to be able to turn and it look exactly like it does now. So if it can't turn 5 times and look exactly the same it does now, then you wouldn't divide it by 5. And so we'll look at that. Okay, and so we're going to look more just at reflectional or line symmetry, just your basic. Remember, it's just if you draw a line and it reflects onto itself. So I'm going to draw all the lines of symmetry here. I'm going to do it pretty quick. So in this triangle, notice this is just an isosceles triangle. It is not an equilateral. So the only line of symmetry here would be this line. Okay, then we have this M. Draw it straight down the middle. We have a hexagon here, and this really isn't drawn to scale, but it should be. Assume this is a regular hexagon, then I could draw all types of lines. I could draw here, here. I could even draw here, here, and then I could even split these in half one more time. So again, this is really bad because I'm doing this on my laptop, but you get the idea. Okay, if you look at this parallelogram, there is not going to be line symmetry here. There's nowhere where I could draw a line, and if you were to fold it over, it would look exactly like it does now. There's none. Okay, and so here, if it's just asking if it has line symmetry, the answer is no. There's no lines of symmetry. Okay, here we have this football, so you draw your line right down the middle. We have a car. It just has this one line. And then we have this tulip-looking flower, and so I could draw a line here to make that line symmetry. Okay, so that's your first time with symmetry is line symmetry. The next kind is going to be rotational symmetry, and I kind of talked about this before, but you will have rotational symmetry if you turn or rotate your object and it maps onto itself with less than 360 degrees. So if it takes a full turn for it to look the way it does right now, then it does not have rotational symmetry. So I'm going to kind of show y'all the best I can with this. If I click on this triangle and it's showing you that it's an equilateral, now I hope this is drawn to scale, but I can't promise that it is. So if I were to rotate this, okay, notice, and this is going to be hard to visualize, but if I rotate it 1, 2, 3 times, I was able to rotate it 3 times, and every time it had the same, it looked exactly the same. It was mapped onto itself. So does this have rotational symmetry? I would say yes. And if I want to get the degree or the angle of rotation, then I would do, in this case, 360 divided by 3. And so the degree of rotation here, the angle of rotation, would be 120 degrees. Okay, then we move on to this, looks like a square, right? It doesn't tell you that, but let's just say it is for kicks and giggles. And so if I were to rotate this baby, and I just moved it, if I were to rotate it and I were to turn it 1, and this is not working. I'm pretty sure I just changed the size of it. You get the gist here. If I were to turn it 2, 3, 4 times, every time I turn it, it would look exactly like it does right now. And so, yes, this does have rotational symmetry. And here I would do 360 divided by 4, and that would get me 90 degrees for my angle of rotation. Okay, then we're back to this parallelogram, and we said that this parallelogram does not have line symmetry, but that does not mean that it doesn't have rotational. And so if you think about this parallelogram, if I were to rotate it, it would look exactly the same. I'm really trying my best here, y'all. Sorry. It would look exactly the same if I just turn it 180 degrees. Okay, but if I were to turn it 90 degrees, it would look like this. Okay, and that's not going to work for us. We need it to look exactly the same as it does from the beginning. So a 180-degree turn, and it's going to look exactly like it did. And so I can only turn this thing 2 times for it to get back to its original. Okay, it was one time at 180 degrees and then another time full 360. So in this case, this is 3, so yes. And this would be 360, and then it only had 2 turns to get back to its original. And so this would be an angle of rotation of 180 degrees. Okay, then we have this circle. And you think about this circle, anywhere you turn it, however much you turn it, it keeps mapping onto it. Oh, sorry, I skipped the A. The A, if you turn the A, it's not going to look like itself until it gets all the way back around. So even though this has line symmetry, this does not have rotational symmetry. No rotational symmetry here. Back to the circle, as you rotate the circle around, it always is mapping itself. Okay, and so in this case, we could say, if we wanted to put an actual degree number, we could say it's turning every 1 degrees, but there's degree measures in between like 0 and 1. Like there's 0.001 and 0.002 degrees. And so here we'll just say yes, and we'll say that there's an infinite amount. Okay, basically that should say infinite in between 0 and 360, but we'll just say yes, infinite. Okay, then we have this pentagon, and it doesn't tell you it's a regular pentagon, but let's assume that it is. If it is regular, then I would be able to turn it 5 times, and every time I turn it, it would map itself onto the original. And so here I would say yes, and if I do 360 divided by 5, it's 72 degrees. Okay, here's the heart. This heart looks a little bit better than mine. So here, again, we knew that there was line symmetry, but if I tried to rotate this around, it's not going to look like itself until it gets all the way around. And so here, this does not have rotational symmetry. Okay, and then we have this, I don't know, Tetris looking object. And so if I were to turn this, let's see how many times we can turn it. I can turn it 1 and then 2 to get it back around to its original. So if I did 360 divided by 2, then that would be 180 degrees. Our last type of symmetry is point symmetry. And remember, this is if it is exactly 180 degrees that maps the figure onto itself. So we're going to see if these have point symmetry. We just did some of these on the slide before. So I'll just remind you that this equilateral triangle, we got the degree of rotation to be 120 degrees. Okay. If it can't be 180, if it's not exactly 180, then it does not have point symmetry. So no point symmetry. The next one was the square. And we said that the angle of rotation was 90 degrees. But if I do that 2 times, 90 and 90, that is 180 degrees. So this does have point symmetry. Okay, then we had a parallelogram, and we said this one is easy because we said that it could only turn 2 times to get back to its original. And so this one was exactly 180 degrees. So that's an easy one. That's yes. Okay, then we look at this eye. And if I turn this eye 180 degrees, that's not working real well. But if I turn it 180 degrees, it's going to look exactly like it does now. And so we would say yes for this. And then the circle, again, we said infinite, but if I were to turn it 180 degrees, it is going to look exactly like it does now. So yes, the circle does. So I mentioned this earlier when I was going through the definitions, but if a figure has point symmetry, it is also going to have rotational. So if it does have exactly 180 degrees, then that must mean it has rotational. And so that's going to bring us into this next slide. And I am not going to do all of these. I'm just going to pick a few to do. And it wants you to list all types of symmetry, and then draw the lines of symmetry and or give angle of rotation when needed. Okay, so A says this is a non-regular hexagon. So 6 sides, but they're not all the same. Okay, and so there is symmetry here. Okay, there is line symmetry. Sorry, I should get more specific with that. There is line symmetry here. We would have that line, and we would have that line. And so the next easiest thing, honestly, is to figure out the rotational. Okay, and so I would do 360 divided by, now here's what you have to think of. If you were to rotate this, okay, how many times would you rotate it? It's not going to let me rotate that hexagon, but how many times would you be able to rotate it and it looks exactly like it does now? It would only be 2, okay, which means the angle of rotation here is 180 degrees, which means this has line symmetry, this has point symmetry, and if it has point symmetry, it must also have rotational symmetry. Okay, I'm just going to hit on, let's say, I don't know, let's look at F. Okay, so F, we have this S here. Okay, this S does not have line symmetry. There's nowhere I can put a line and cut it in half. But if I were to turn this S 180 degrees, it would look exactly like an S still. And so I would say yes to point symmetry because it's exactly 180. And then, of course, we would say rotational because our angle is 180 degrees. Okay, if you want to go through more of those examples here, just pull up the class notes for this stuff. Okay, this next question says we have an isosceles triangle ABCD. I'm going to move some of this stuff so I can make this graph bigger. So ABC with base AB, given A is at 3, 2, and B is at 7, 8. What is the equation of the line of symmetry? And I'll just kind of walk through this one, may not do it all. So I have A is at 3, 2, and B is at 7, 8. Okay, so we have these 2 points on here. And so we have this line right here that is going to be the base of our triangle. And so we don't know if this triangle, we do know it's isosceles, and this is the base, but we don't know if this triangle goes out this direction or if it goes out this direction. The good news is it doesn't matter, okay? Because the same line of symmetry is going to cut that in half. So it does not matter, okay? So I'm going to undo that so that we can figure this out. And so think about what that line of symmetry is going to do. It's going to cut that base in half. And so one thing that we would need to do is figure out what the midpoint of this is. Okay, so if I were to do that, this goes up 6/4. And so so half of that would be up 3/2. And so that point right there would be at, let's see, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So that would be at 5, 5. Okay. And then we would need to figure out at that point, if this is an isosceles triangle, at that point, those two lines would be perpendicular. And so if I figure out what the slope of AB is, then I can figure out what the slope of my perpendicular line would be. So I would say that the slope of AB is up 6/4, which is 3/2. And the opposite reciprocal of 3/2 would be -2/3. So the slope of this line is -2/3. So I could just keep graphing this. So I could go up 2/3, up 2/3. Actually, this one comes out to be nice. You don't even have to put this in a formula or anything. Oh, actually, I just graphed that wrong. So you do need a formula because it would look like this. So notice that that y-intercept is not perfect. And so I'm not going to take the time to do this, but you would have your point and you would now have your slope. And so you could write the equation of that line of symmetry, either using point slope or using y = mx + b. The answer to that, if you do want to work through it, is y = -2/3 x plus 25/3. Which makes sense because that is about 8 point something, and that's where our y-intercept is lying. All right, so I'm going to move some of that out of the way. This question here is pretty simple. I'm going to give you the answer because I think it's really easy. It says, which of the following statements is false? So the one here that is going to be false is going to be B. So if you want to take the time to do that one, just says, these are talking about where the line of symmetry is. It's not hard. Okay, here's our favorite types of questions: always, sometimes, and never. And so here, figures that have point symmetry. So think about what point symmetry meant. That was when it was 180 degrees. So if it has point, it must also always have rotational. So this first question is always. Number 2, figures that have rotational. Now think about rotational, what that means. Okay, it's not necessarily 180 degrees. Think about the equilateral triangle. It was 120 degrees. But for point symmetry, it has to be 180. Okay, so it could have 180 or not necessarily. And so that one's going to be sometimes. Number 3, a triangle blank has 3 or 1 line of symmetry. Okay, well, that would be sometimes. Okay, because you could actually have a triangle that has no lines of symmetry. Okay, if you have a scalene, weird-looking triangle, it's not going to have any lines of symmetry. Number 4, a regular polygon blank has lines of symmetry equal to the number of polygon sides. Okay, that would be always. Think about when we looked at that regular pentagon or regular hexagon. We just divided it by the number of sides, or number of, polygon sides it had. And then number 5, a parallelogram blank has 2 lines of symmetry. This would be sometimes. Now, here's where you have to shift your thinking a little bit, because I know what we're thinking. We're thinking parallelogram is this, okay? And you're not wrong. But what else is a parallelogram? A parallelogram is also a square. A parallelogram is also a rectangle. And it's also a rhombus. And so we have to remember that parallelogram doesn't just apply to this first figure, and that's why that one is sometimes. Okay, the last part of today, we're going to be talking about dilations. And a dilation is a similarity transformation. Okay, it's a similarity transformation. So the shape remains the same, but the size may change. Okay, just similarity. And we're going to look at a scale factor. We've already looked at scale factors many times this year, but it'll describe the size change. And here's how you can get your scale factor. If you take the new image and you divide it by the old image, so the image divided by the pre-image, then that can get you your scale factor. The pre-image and the image are collinear. Okay, you're going to see why that's important here in a couple minutes. Okay, if you have a scale factor that's greater than 1, that's because your dilation is called an enlargement. If your scale factor is equal to 1, the pre-image and the image are congruent. This is called isometry. Okay, isometry when it's the exact same image. And then if your scale factor is less than 1, that's because there's been a reduction in the image or a shrink. The notation that we're going to look at for this, you can see here. So let me explain that. That capital D means dilation. The lowercase c, that's your center of dilation. Normally, you're going to see it at the origin, and you hardly have to even think about it at all. But you are going to see an instance where it might not be at the origin. Okay, and then S is going to be your scale factor. So we'll see that dilation here. So dilate the shape having the origin as the center of dilation with a scale factor of 2. If it says the origin as the center of dilation, hardly even think about it. It is not a big deal. Don't let it confuse you. I'll show you what that means here in a minute. So scale factor of 2 and use prime notation. And so I will show y'all what I do because I don't want to screw this up. What I would come over here and do is I would write the original points. Okay, and there's no letters on this. So let's say this is A, B, and C. So what I would come over here and do is I would say A, B, and C. Okay, because I don't want to do this in my head and screw something up. So A is at 2, 3. B is at -2, 2. And C is at -5, -5. Because now, if this is a scale factor of 2, all I have to do is multiply all those points by 2. That's it. So A prime would be at 4, 6. B prime would be at -4, 4. And C prime would be at -10, -10. So again, all I did was multiply these points by 2. And I'll show you, you don't necessarily have to graph this, but I will show you what this would look like and what I mean by center of dilation. I'll show you on this one, and then I won't do it again. But if I plot 4, 6, okay, this is where A prime would be. And then let's say I plot B at -4, 4. So this would be B prime. Okay, I'll just do those 2 points. It doesn't matter. Okay, if I were to connect, because remember we said that these points are collinear. If I connect these two A points, okay, so I'm connecting those A points. Okay, and let's say I connect these B points also. Look at where those 2 lines cross. They cross right here, right in the center. So that's what that means. If you were to connect your image and your pre-image points, those lines are going to cross at the origin. So that's what that means. B says if the scale of dilation is 3 to 1 and A is 4, -5, what is A prime? So if it helps for you, sometimes these ratios get confusing. If it helps for you to put it like this, 3 to 1, because now you can see 3 divided by 1 is 3. And so that'll tell you here, oh, I need to multiply both of those numbers by 3, and that would be 12, -15. C, if the scale of dilation is 1 to 3 and A is 4, -5, what is A prime? So again, if it helps for you to put that as a fraction, now notice this here is 1/3. And so I need to multiply both of these numbers by 1/3 instead of multiplying them by 3. So 4 times 1/3 would be 4/3. And negative 5 times 1/3 would be negative 5/3. And that would be my new point. D says, what is the scale factor of this dilation? And so what I would do, again, this is what I mentioned earlier, I would write down your points. And so I'm going to look at A, I'll just use A for this. And so A, if I get that point, that's at negative 5, 5. Negative 5, negative 5. Sorry. Okay, negative 5, 5. And then if I get the ordered pair for A prime, and we're just going to assume, I think that's at negative 2.5 and 2.5. Okay, what I'm going to do is I am going to take the image and I'm going to divide it by the pre-image. Okay, so if I just say take the x values, okay, because they're going to be the same. So if I do negative 2.5, that's the image, divided by the pre-image, which is negative 5, then that would give me 1/2. And so the dilation here, the scale factor, is 1/2 or 0.5. It doesn't matter. E says, what is the scale factor of this dilation? So again, I would do that same thing. If you want to do this yourself, you can, but you'll see that the scale factor of the dilation is 2, okay? Or you can say 2 to 1. And it doesn't tell you what the original is. I'm saying that the dashed rectangle is the original, and then it got bigger. I could say it was 1/2 if I say it the other way around. And then what is the center of dilation? So again, here, if I were to, and this graph is small, and I'm sorry, I guess I could make it bigger real quick. Let me just do that. It'd be easier for me to write on it. Okay, so here, if I were to connect these points here, so I make this line here to connect my A and my A prime, or whatever letter it is. Okay, and then I do the same thing, let's say in this upper right corner, and I connect those two. The center of dilation is going to be where those two lines cross. I could do all 4 points here. I'm just not, because it doesn't matter. And so here, the center of dilation would be at 0, 2. So this one's not at the origin. Okay, and then we are actually going to be done, because the rest of this, we would want you to have a ruler, or some things this unit, even a protractor for, and you don't necessarily have those things at home. And so we are going to be done.